Alright, let's take a look at our lesson on sequences. The very top part of this is review. We'll get to the calculus part in just a moment. We did some preliminary work on sequences and series in pre-cal and maybe a little bit in algebra 2. We're going to take that and run with it. Alright, so up here in the corner over here we just have some examples of sequences. We need to be sure that we have a clear distinction between the concept of sequence and the concept of series. We're actually going to spend one day on sequences and all of the rest of the days in the unit on series. So sequences is a list of terms. It's basically a compilation or a list of terms that will have some kind of a formula, typically some kind of an nth term formula that could be used to create the terms. These things aren't added together, they're just a list of terms. N stands for the term number. On this formal definition down here we have a sequence that is a function whose domain is the set of positive integers. The sequence is symbolized by this nth term. The subscript n is always understood to start with a 1. And it only includes positive integers. Okay, so that's kind of a review from last year, what a sequence is. If we were to graph a sequence, it would be basically points, individual points. It's not a continuous thing. If we went to the number 1, when n is 1, we would put the value of the first term. If we went to number 2, when n is 2, we'd plot the value of the second term. It will be just individual points. It's not a continuous thing. So that's what it would look like if it were graphed. This is called brace notation. It's just a way to write a sequence, just notation that you should be familiar with. Alright, as another reminder from last year, it would be handy if you remembered what the nth term formula for an arithmetic sequence was. I'm going to write it up here for you. Be probably a good idea. So a to the n equals a to the 0, that's our first term, our initial term, plus d stands for the common difference, times n minus 1. And that's just a reminder of our formula for arithmetic. We also had a formula for geometric sequence, which was a to the n equals, and then we had our first term, a to the 0. R is our common ratio to the n minus 1. Now on this one, I just want to make a statement about this one. The n minus 1 is the normal standard way to write a geometric sequence. It doesn't have to be n minus 1. It could be just n, or it could be n plus 1. Don't let that throw you off. Really, any of those configurations is fine for a geometric sequence. Alright, so let's talk about convergence. A sequence converges basically if, as we approach infinity, as n approaches infinity, we head towards a one particular number. We have, which they're calling L. So, it converges if we head to one particular number. If the limit does not head to one particular number, let's say it either oscillates or it heads to infinity or negative infinity, then it diverges. Now, it's really important to understand what this is saying. This is not saying that if I take the limit of a sequence, an nth term sequence, and I get a number, that's what my number would be if I added them all up. That is not what that says. What that says is this is the number as the pattern keeps going, whichever the pattern is. As the pattern keeps going to infinity, each number will get closer and closer to one particular number. That's what this would show. Each number would get closer and closer to one particular number. That's what this stands for. Another thing that's going to be pretty important to us is this second theorem right here. And that tells us that a sequence converges to a limit L if and only if the sequences of even numbered terms and odd numbered terms both converge to the same number. Now, we're going to be dealing with this theorem when we have a sequence that alternates positive, negative, positive, negative, positive, negative. We're going to have to break that sequence down into two sequences, one with all the positive terms and one with all the negative terms, and deal with them separately so we can get a better feel for what's going on. That's what this theorem is used for, is when we have that situation. All right, so let's go this last theorem, just kind of have it up there. The absolute value of our sequence, if that goes to 0, then the whole with that non-absolute value will go to 0. Okay, and this is just to do with sequences. All right, remember series is where we take these numbers and we add them all up. Remember series was a sum, it's a summation. All right, let's go to undo some examples. So I tried to get a variety of different examples for us to work through. Certainly this is not exhaustive. It's impossible for me to show you one of every kind. I tried to get a sampling so you would have an idea, a better idea of the procedure. So let's take a look. It says, determine whether the sequence converges or diverges. If the sequence converges, find its limit. If the sequence diverges, show why. Basically what that boils down to is we're going to take each one of those nth term sequences and we're going to do the limit to infinity. We're going to be able to tell by the limit whether it converges or diverges, and we'll be able to show why by the limit. That's what we're going to be working through. All right, so in order to work with the limits, I need you to recall the rates of growth that we've talked about several times. You have those rates of growth on your yellow sheet. Those are going to become very important to you, a daily thing that you're going to be working with in these next couple of units, are the rates of growth. All right, so I'm going to show you a couple of different ways to do the first example. Whichever way is more appealing to you, that's the way I would stick with if I were you. First of all, I really do not like working limits with the n-1. It kind of muddies up stuff. It troubles me. So what I do is I simplify it first. We've done this often where we go backwards from this and we split it apart into two different pieces. So I'm just going to do a little bit of algebra work over here before I start the limit. We're just going to do a little bit of work. So I'm going to split this apart into 1/2 to the n times 1/2 to the -1. I would really prefer working with just the n power instead of any kind of weird configuration. This 1/2 to the -1, we should know, and I'm sure we all do, that we can write that as 2. So this really, I'm going to be working with 2 times 1/2 to the n power. That's what I'm going to be taking the limit of. I just wanted to, this is what I would prefer to do. So limit as n goes to infinity. And the reason that we're going to infinity is we can't go to negative infinity, right? The n's have to be positive, so it would make no sense to go to negative infinity. We are going to infinity of 2 times 1/2 to the n. All right, there are two different ways that we can work this. I'm going to show you both. One is algebraic, and the other one is using rates of growth. Okay, so I'm going to do the algebraic one first. This is the same thing. So 1/2 to the n is the same thing as 2 to the -n. Would we agree with that? That's the same thing. Again, this is like algebra work over here. So this would be like 2 to the -n. And rewriting that, we know that can be rewritten as 1/2 to the n. Okay, so we can think about the limit in algebraic terms like this. And we can use that property when I put larger and larger numbers in the denominator, it tends to 0. Okay, so that's one way that we can think about this limit, is algebraically. Another way that we can think about this limit is with rates of growth. Okay, so let's think about it. Instead, let's think about it as 2 times 1 to the n over 2 to the n. And let's think about the growth rates of these two right here. Will the numerator or denominator grow faster? The denominator is going to grow faster, isn't it? And over time, it's just going to wipe out. I mean, it's just going to be gigantic, right? And the numerator, I'm hoping we all know that 1 to infinity is not infinity. It's an indeterminate form. I can't do 1 to infinity. But I can look at it with rates of growth. And so the rates of growth, this denominator is going to grow faster, which means, according to the rates of growth, it's going to tend to 0. So two different techniques of the ways to look at this limit. Of course, you don't have to write any of this work. You know, if you can see the limit and then just write the answer, I would just caution you with jumping to conclusions. We don't want to jump to the wrong conclusion. So you do need to think through one of these types of techniques before you write the answer. So since this converges to one particular, it converges because the limit equals one particular number. So the first example converges. Let's do this one here underneath, and I'm going to work this one using the rates of growth. If we have 3 to the n over 5 to the n, is the numerator or denominator going to grow faster? The denominator, so this is going to tend to 0. So this one converges. Okay, let's do the one right next to it. The limit as n goes to infinity of 5 to the n over 3 to the n. Okay, is the numerator or denominator going to grow faster? The numerator is. So that means this one is going to tend to infinity, which means this one diverges. Okay, and that's that pattern. We're going to go to this one. It's along the same pattern, trying to show you several different types of the same pattern. And actually here, I can fill this part out right here with these two pieces of information. This is a geometric sequence with an r that is less than 1. Remember that from last year? And we know that geometric sequences with r's, absolute value of r that's less than 1, do converge. So, and this one is a geometric sequence with an r of greater than 1. And this limit, our thought process shows that if absolute value of r is greater than 1, then the geometric sequence diverges. Okay. So let's take one last look at geometric sequences in this fourth example right here. This one is a bit different because it is an alternating sequence. It goes positive, negative, positive, negative. It switches signs. So what I'm going to have to do is I'm going to have to break this apart into even terms and odd terms. Okay, really important that you go through this procedure because sometimes these converge and sometimes they don't. Really just depends. So let's think about what that is. First of all, it alternates. The piece that is the troubling piece is this negative. We can think of it as a -1. What I'm going to do is I'm going to break that apart from this main part. I'm going to work some algebra first before I break it into even and odd. So I'm going to break it apart. It's going to be -1 to the n minus 1 times 1/2 to the n minus 1. I'm just going to break that apart. And we already dealt with 1/2 to the n minus 1 over here. Remember that? I would write it as 2 times 1/2 to the n. So I have this alternating part here on the outside, and I'm going to rewrite this piece as 2 times 1/2 to the n. Okay, so I've done some algebra work to it. Now let's really investigate and pull this apart. I will tell you the confusion that we had earlier. I'm going to talk through the confusion as we're working through it because there were some students that were having some difficulty earlier. This n right here is going to stay an n. I'm not going to be able to take that off. This is the piece that I'm working on because I want to separate this into positive terms and negative terms. I want to do even terms and odd terms because it alternates, right? Every other. So this n is going to go away when I split it into pieces. Okay? This n is going to stay. This is the n I'm going to be working with because it's the alternating part. Okay? So let's work on the alternating part. Let's do the even. No, let's see, what do we have? Oh, I have written the odd part first. Doesn't really matter. Let's break it into odd and even. All right, so let's think through the procedure here. Odd numbered terms are where n is 1, 3, 5, 7. Okay, odd numbered terms. So if I put an odd numbered term in here, like 3 minus 1 is 2, that would make this positive, wouldn't it? Every time. Every single odd numbered term will make this positive. Are you with me? So I am going to write this. We're going to do the limit as n goes to infinity of the 2 times 1/2 to the n. Those are all the odd numbered terms grouped together. Now, if I put even numbered terms, such as, n is 2 or 4 or 6 or 8. If I put even numbered terms in here, what happens to this sign? It's going to be negative, isn't it? -1. So I'm going to take this and I'm going to do the limit of it of a negative one of these. Now notice, I still have an n. I still have this n. That doesn't go away. Why did this n go away? Why did it go away? Well, because I split it out, right? I wrote it as, instead of writing it as one complete sequence, I wrote it as a sequence of even terms and a sequence of odd terms. All of the even terms are negative and all the odd terms are positive. I don't need this alternating piece anymore. That's the whole purpose of this technique, is so that we can investigate them separately. All right. So if we think about this as rates of growth, 1 to the n over 2 to the n, what are we going to tend to? 0. If we think about this in terms of rates of growth, -2 times 1 to the n over 2 to the n, what is this going to tend to? It still tends to 0, doesn't it? Whether I'm multiplying by a +2 or a -2. So since these are the same, this particular alternating sequence converges. Okay, because they go to the same limit. You'll have some that maybe they go to a +1/2 and a -1/2. Or is that going to converge? No, those are different signs, right? They have to be the exact same number to converge, not just going to a number. It has to be the exact same number for the odd and the even terms to converge, right? They both have to go to the same number for the whole thing to converge. All right. Okay, let's leave our geometric sequences and move on to some other things. So we're going to test it out, the limit as n goes to infinity of sine of n. So what's that limit going to do? Yeah, it's not going to exist. Now, it's not going to infinity like this one over here. It basically doesn't exist because of its oscillating behavior. It just jumps back and forth and back and forth. So this is a d and e because it oscillates. And since the limit to infinity doesn't approach any particular number, this particular sequence is going to diverge. Okay? The next one, limit as n goes to infinity of 3n plus 2 over 5n minus 1. We've worked with these rationals before. If you remember when we first started working on these in pre-cal and like at the beginning of this year, we would multiply by 1 over the biggest over 1 over the biggest. Remember that? 1 over n over 1 over n. I'm hoping by now you can just look at it and tell what the limit is. If you still need to do the algebraic work, please do so. But I'm hoping that you can just look at it and tell what the limit is. What is this limit going to be? 3/5. It's going to be 3/5. So what does that mean? That means that this converges. And what that means is that as I put in, more terms, the first term, second term, third term, fourth term, fifth term, as I put in more and more terms, the actual term value is going to approach 3/5. The actual term value will approach 3/5. It doesn't add up to 3/5, okay? The actual term value approaches 3/5. All right, let's move over here. This is an alternating one. For alternating sequences, what do we need to do? We need to break it into even and odd, okay? So we'll put the odd first. We have odd and even. All right, so limit as n goes to infinity, 3 plus. All right, let's think about this as far as odd numbers. So if I put a 1 or a 3 or a 5 or a 7 in, what's my result? A negative 1. Okay, and let's do even. Limit as n goes to infinity of 3 plus. Okay, let's do all the even. If I put a 2 or a 4 or a 6 in here, what happens to this number? It goes to a positive 1. Now this is where students got confused because the n went away. Do we know why this n goes away as in relation to this one? Right? Yeah, because the reason that it went away is because we are actually splitting it into two different sequences. The sequence of all the odd terms and the sequence of all the even terms. That's why the n went away. This will give us a 2 and this will give us a 4. Does this sequence converge? No, it diverges. Now, I mean, we have limits, actual numbers for limits, but that doesn't matter, right? They have to be the same. All right, let's look at this one. Limit as n goes to infinity of ln n over n. A couple of different ways you could do this one. You could do it by L'Hopital, because it's infinity over infinity. If we did it by L'Hopital, it would be what? The limit of n goes to infinity of 1 over n over 1. What would that tend to? 0. Or we can do it by rates of growth. According to our rates of growth chart, what grows faster? A natural log or an algebraic? Algebraic. So since the denominator is growing faster, we go to 0. So either way you would like to do it, it goes to 0, so this converges. All right, we're doing okay? Last one. Factorial notation. I saved this one for last, maybe because of all of the topics that we've looked at today. Factorial notation is probably the one that we have the least experience with. Probably not a lot of experience with factorial notation. We actually have to simplify this factorial notation before we can work with it. We can't work with it like that. And I will tell you what our end goal is. Our goal is to make the factorial notation go away completely. That is always our goal. We don't want it. We can't do calculations with it. So what I'm going to do is I'm going to simplify it. Before I do the algebraic simplification, I want to remind you numerically, and maybe that will help you as I simplify. Let's think of n being 10. Let's just think of n, in this case, being 10. Basically, I would have 11 factorial over 13 factorial, right? And in our head, we could simplify that quite easily. All right, that's really what I'm going to be doing with this, but I'm going to be doing with this in the abstract. Now, some of you, and maybe some of you already can, just go straight to the simplified form of this, and that is fine. But I'm going to take you through algebra so that you can see how it happened. They're not all going to look like this. There are going to be so many different varieties of this. So let me take you through the algebra. If I were to write this out in basically expand it, this would be like 11 times 10 times 9. And let's say I wanted to stop there, times 8 factorial. I could do that, right? Isn't that okay? That's kind of what I'm going to be doing to this. Okay, I'm going to be doing that, but I'm going to be doing that algebraically to this. So in the numerator, and we're just going to simplify it up here. In the numerator here, I would go n plus 1. The next term underneath would be n. And just so you see the pattern, I'm going to keep going. I really don't need to, but I'm going to keep, just so you can see the pattern, what the next one would be. The next one would be n minus 1, and I'm actually going to stop there and leave the factorial on that one. Over, so let's work on the denominator. This would be like n plus 3 times n plus 2 times n plus 1 times n, and just like in the top, I'm going to stop at the n minus 1. If I wanted to add another term, it would be n minus 2. Do we see the pattern? Okay, I just want you to see the pattern of simplification. Now, can we cancel out some stuff? Yeah, we got a bunch of stuff to cancel out, right? And our goal has been accomplished because the factorials are going to go away. See how they're just going to go away. And so are the n's and the n plus 1s. So basically what I'm going to be left with is the limit as n goes to infinity of 1 over n plus 3 times n plus 2. Okay? And so as we look at this limit is going to tend to 0. So this one converges. Okay?